There's a decent chance the most observant creature watching you walk to work this morning isn't another person. It's the crow sitting on the telephone wire, the one that's been quietly clocking your face, your pace, and what you're carrying for longer than you'd probably like to admit. To understand why that matters, you have to understand what crows already were before anyone figured out how to listen to them properly. Because the case for crow intelligence has been building for decades, one uncomfortable finding at a time. Start with the puzzles. Crows solve multi-step problems that require planning several moves ahead, the kind of tasks researchers design specifically because trial and error alone cannot crack them. A crow has to understand not just what action to take next, but what that action sets up 2 or 3 steps later. That is not reflex, that is forward planning. Then there are the tools. Crows do not simply grab whatever stick happens to be lying around. They manufacture tools, bending wire into hooks, selecting specific stick lengths and widths for specific jobs, sometimes modifying an object on the spot when the first attempt fails. This was long assumed to be almost exclusively a primate trait, one of the supposed dividing lines between us and everything else. And then there is the part that should genuinely unsettle you. Crows cache food. If a crow suspects another crow is watching when it hid that food, it will come back later, often when nobody's around, and move the stash to a new location. Sit with what that actually requires. The crow has to track not just where the food is, but what another individual saw, and then act specifically to defeat that other individual's knowledge. Psychologists call this theory of mind the ability to understand that another creature has a perspective different from your own, complete with beliefs that might be wrong and that you can deliberately exploit. For most of scientific history, this was treated as one of the clearest dividing lines in cognition, reliably documented only in humans, and, in a more limited form, a handful of our closest primate relatives. A crow rearranging its hidden food because it remembers being watched is not running on instinct. It is modeling what is happening inside another bird's head. And once you accept that crows are doing that, the question stops being whether they are capable of something like thought. The question becomes how much of what they are thinking we have simply never been able to hear. Then there's the matter of faces. Crows recognize individual human faces and hold on to that recognition for years. In a now well-documented set of studies out of the University of Washington, researchers wore a specific, distinctive mask while trapping and banding wild crows, an unpleasant experience from the bird's point of view. Years later, crows that had never personally been trapped, including young birds and crows from neighboring territories who'd had no direct encounter with the masked researcher at all, would scold and dive at anyone wearing that same mask. The fear had been socially transmitted, parent to offspring, neighbor to neighbor, passed along not through genetics, but through observation and teaching. That's not instinct in any simple sense. That's culture, in the precise scientific definition of the word. Learned information moving across generations through social channels rather than DNA. And yet, for all of that documented cognitive sophistication, for decades of careful behavioral observation, there was a glaring gap. We had almost no real insight into what crows were actually saying to each other while they did all of this. The intelligence was visible. The communication that almost certainly underpinned it was, for all practical purposes, invisible. That gap is what the new research finally starts to close, and the reason it took this long has as much to do with the limits of recording technology as it does with the birds themselves. The research centers on a population of carrion crows in northern Spain that's been under close observation for years by behavioral ecologist Daniela Canestrari, working alongside her colleague Vittorio Baglioni at the University of León. This particular population is unusual even by crow standards. Most European crows pair off and raise chicks as isolated nuclear families. But this Spanish population practices what biologists call cooperative breeding, where extended family groups, parents, older siblings from previous breeding seasons, and occasionally more distantly related birds absorbed into the group all share the work of raising each new generation together. The division of labor is real and consistent. One bird guards the nest while another forages. Guard duty rotates through the group. Feeding gets coordinated, and the family makes collective decisions about when to confront a threat and when to retreat. This is not loose flocking behavior. It's genuine cooperative social organization, the kind that, by any reasonable biological expectation, should require sophisticated ongoing communication to actually function. Canestrari had suspected for years that it did. What she lacked was a way to actually listen to it. What she needed was a way to listen from inside the conversation itself. That's where the partnership with the Earth Species Project came in. Researchers fitted the crows with miniaturized biologgers, lightweight enough not to meaningfully affect flight or behavior, carrying high-fidelity microphones, motion-tracking accelerometers, and onboard storage capable of recording for extended periods directly from the bird's own vantage point, from inside the family unit, at ground level, right at the nest. Before any of this data was used for the main study, the team spent hundreds of hours reviewing nest camera footage, specifically to confirm the devices weren't measurably altering crow behavior or breeding success, a serious and necessary piece of due diligence for any study claiming to capture natural behavior. That number alone deserves a moment because it's not 127,000 instances of the familiar loud caw cataloged from a distance, the kind of thing researchers have been recording for decades. It's 127,000 distinct sounds, automatically detected and isolated, the overwhelming majority of which had simply never been properly captured before, because nobody had a microphone close enough, for long enough, in the right place to catch them. And the very first finding, before researchers had even begun digging into what individual calls might actually mean, reshaped the basic picture of crow communication. The vast majority of those 127,000 vocalizations were not the loud, far-carrying calls that have defined the scientific literature on crow communication for decades. They were quiet, soft. Close-range murmurs, exactly the kind of sound that would be functionally invisible to a microphone positioned even a short distance away. Low and intermediate amplitude calls weren't a minor exception in crow social life. They were the overwhelming rule, dominating the entire vocal record. The famous loud call, the one everyone recognizes, turns out to be just the surface layer, the shout. Underneath it, constant, dense, and entirely undetected until now, appears to be the actual texture of crow family communication. It's worth sitting with what that means methodologically, because it reframes essentially the entire prior body of crow communication research. Scientists studying crow vocalizations have, for decades, effectively been studying the equivalent of a community's loudspeaker announcements, the alarms, and the public calls, while remaining completely unaware that the real social fabric was being woven through quiet exchanges happening at much closer range, the kind of conversation that never reaches a distant microphone at all. The earlier data wasn't wrong, it was radically incomplete, and the missing piece may turn out to be the part that mattered most. This finding immediately changes how seriously researchers have to take crow cognition. A rich, predominantly close-range vocal life implies a social world with real intimacy and relational depth behind it. Cooperative breeding doesn't run on occasional loud alarm calls. It runs on continuous, fine-grained coordination between individuals who track each other's tendencies, history, and current state. A quiet murmur passed between two adult crows at the edge of a nest is very likely carrying specific, contextual, relational information, and both producing and correctly interpreting that kind of signal requires real cognitive sophistication, the capacity to encode meaning into a sound, transmit it through a channel specifically suited to close social interaction, and have it received and decoded on the other end in a way that produces appropriately coordinated behavior. By almost any honest definition, that's what communication does. That's a piece of what language does. And it turns out crows have apparently been doing it constantly in a register we simply had no instrument capable of detecting. The Earth Species Project isn't only working on crows. Parallel research programs run on beluga whales, elephants, several songbird species, and a growing roster of other socially complex animals, all using the same underlying philosophy. Train AI tools, originally built for finding structure in human language and human audio, on the recorded vocalizations of other species, and see whether meaningful organizational structure shows up. Across all of these projects, the same hypothesis keeps gaining support, that the deep logic of communication, how information gets packaged, transmitted, and received, might be a far more universal feature of social intelligence than we've historically been willing to credit other species with. Nature LM Audio, the large audio model the Earth Species Project has built and released as an open-source research tool, is probably the clearest technical expression of this idea. It functions in a way roughly analogous to the AI systems behind human speech recognition and machine translation, but instead of being trained on human language, it's trained on bioacoustic data, recorded vocalizations from hundreds of species across dozens of ecosystems. The underlying bet is that if you expose a model to enough examples of an animal communicating across enough different contexts, it will start identifying which sounds consistently carry meaningful information, which combinations of sounds reliably precede particular behavioral outcomes, and which acoustic patterns cluster together under which conditions, in a way that maps onto the underlying structure of that species' social reality. Not translation in the dictionary sense. something closer to mapping form to function, sound to meaning, signal to the part of the world it actually encodes. What researchers keep finding as these models improve is that this mapping process surfaces structural patterns that look genuinely similar to ones linguists have identified in human language, not the specific words or grammar, but the combinatorial logic, smaller units assembling into larger ones to produce meanings that no single unit carries alone, the referential capacity to indicate specific individuals or states in the world, and the social embedding where meaning shifts depending on the relationship and history between the two communicators. None of these are features humans invented from scratch. Increasingly, they look like features of communication itself, arrived at independently by different evolutionary lineages because they're efficient solutions to the same underlying problem, coordinating complex social behavior between intelligent individuals. The pattern shows up well beyond crows. African elephants use individualized calls for specific members of their social group, functioning much like names, a finding that's been independently documented by multiple research teams studying elephant vocal behavior. Common marmoset monkeys appear to do something comparable. Sperm whales produce clicking patterns called codas that differ systematically between distinct social clans in ways that function almost like cultural dialects. And crucially, those dialects are learned rather than inherited, with young sperm whales picking up the vocal patterns of the group they're raised in, the acoustic equivalent of a child acquiring their community's accent. And now crows, arguably the most thoroughly studied non-primate cognitive specialists in the animal kingdom, turn out to have a vocal life substantially richer and more structurally complex than anything previous recording methods could access, prompting researchers to openly reconsider baseline assumptions about corvid communication that the field had settled into. It's worth being careful here, because the history of animal cognition research is genuinely littered with cautionary tales of overclaiming, of researchers reading human-like meaning into animal behavior because they wanted it to be there, rather than because the evidence actually supported it. The scientists involved in this work are themselves explicit about that risk, and careful not to leap ahead of what the data currently shows. Nobody is claiming crows have a language in the full human grammatical sense, and the specific meanings of individual crow vocalizations remain for now genuinely under investigation rather than decoded. What's actually been established, solidly, is narrower but still significant. Crow communication is vastly more frequent, more acoustically complex, and more dominated by quiet, close-range exchange than any previous research method had revealed, and the tools now exist to start systematically mapping what that hidden layer of communication actually does. There's also a less flashy but genuinely important story underneath all of this about what the AI is actually contributing technically. Bioacoustics research has historically been bottlenecked not by a lack of recordings, but by a lack of capacity to process them. You could record as much wild audio as you wanted, but you could only extract usable information from the portions a human expert had manually listened to, labeled, and classified. An approach that's slow, expensive, and scales terribly against the volume of data modern biologging hardware can now generate. VocalBoxen's contribution is removing that bottleneck. It doesn't replace the biological expertise needed to interpret what a vocalization means. That part still requires careful, conservative scientific judgment, but it automates the prior step, detecting and isolating which sounds are even present in a dense, overlapping recording, at a scale and speed no team of human annotators could realistically match. That's the unglamorous but genuinely transformative part of this story. A methodological bottleneck that has limited the entire field of animal communication research for its whole existence is finally being lifted, not just for crows, but as a reusable open source pipeline. Other research teams are already extending to new species and new questions. The timing of all this isn't a coincidence either. It reflects a convergence of several technologies maturing at roughly the same moment. Miniaturized electronics have reached the point where a biologically tolerable data logger can be built small and light enough to attach to a medium-sized bird without compromising its welfare or behavior. Battery technology has improved enough for those loggers to run continuously in the field for extended stretches. Cloud storage and computing have made it practical to store and process the sheer volume of audio that long-term biologging generates. And deep learning architectures, descended from the same transformer-based approaches that transformed human natural language processing, have proven able to find structure in complex, high-dimensional audio data that no earlier computational method could reliably extract. Individually, each of these developments mattered. Pointed together at the specific problem of animal communication, they add up to something genuinely new. So where does this actually leave us, and why does it matter beyond crows specifically? If continued research confirms that crow communication carries real structural and relational complexity, and the early findings strongly point that direction even if the full picture isn't settled, it has real implications for how we think about our ethical relationship with them. It becomes harder to treat them as simple biological mechanisms producing reflexive, hardwired signals. It means acknowledging that we share urban and rural space with animals that appear to have something like individual perspectives, that communicate actively about those perspectives to specific other individuals they have ongoing relationships with, and that have, for the entire span of human civilization, been attempting to coordinate complex social lives in an acoustic register we simply lacked the instruments to perceive until very recently. There are practical applications, too, beyond the philosophical weight of the finding. Better understanding of how socially complex species communicate could meaningfully improve conservation work, potentially offering early warning signals of ecosystem stress encoded in shifting vocal patterns among sensitive species, long before those stresses show up in more obvious ways like population decline. It could also inform how we design and manage shared urban and rural spaces in ways less disruptive to the communicative, social lives of the species we live alongside without ever really noticing. But underneath the practical applications is something harder to quantify and arguably more significant. For most of human history, we've operated on something close to an unspoken assumption that meaningful, structured communication, the kind built on relationships, memory, and context rather than pure reflex, was something that set humans apart, with maybe a narrow allowance for our closest primate relatives. What's accumulating now, study after study, species after species, beluga whales, elephants, sperm whales, and now crows, is evidence that this boundary may have always been thinner and blurrier than we assumed, less a hard biological line, and more a reflection of the limits of our own recording equipment and attention. The crow on the telephone wire was never silent. It was having a constant, quiet, structured conversation with the family members around it the entire time. We just didn't have a microphone close enough, or sensitive enough, or paired with the right kind of pattern recognition tool to hear any of it. We still don't know, with full scientific confidence, exactly what any specific quiet crow call means. That work is ongoing, and the researchers involved are appropriately cautious about getting ahead of their own data. But for the first time, there's solid, peer-reviewable evidence that those quiet calls mean something at all, that they're not noise, not overflow, not incidental byproduct, but a dense, functioning communication system that's been running in plain sight, or rather plain hearing, this entire time. The tool's being refined right now in field stations in northern Spain, in computational labs at the Earth Species Project, across a growing international network of collaborating research groups, are getting incrementally closer, season after season, dataset after dataset, to actually being able to tell us what's being said. What we choose to do with that understanding, once it fully arrives, may turn out to be one of the more quietly significant questions of the coming decade.